Differential equations have to do with differentiability. This word here has to do with the derivative operator, taking derivatives of functions and expressing certain formulations in terms of equations, and those equations will involve derivative operators. So there are multiple ways of denoting the derivative of a function. We're going to, in this introduction, refer to the quotient notation for derivatives and to the prime notation for this operator. The quotient is convenient, at least in my opinion, in the sense that when we use this notation, we always use this letter D, and we, in the denominator of this quotient, would always specifying the variable we are differentiating with respect to. By writing dy dx, we are assuming that y is a function of the variable x. Okay, this right hand side here, f of x comma, don't worry about that. That's something that's like a placeholder for now. But we're simply referring to the notation. So this quotient notation, also named after Leibniz, it's going to be convenient to specify exactly what is the variable of differentiation. The other type of notation is much more convenient in certain scenarios where you're writing long expressions, and so long as is not ambiguous, what is the variable of differentiation, we can write simply prime, differentiating prime, meaning that that is one derivative, right? So here on this example of prime notation, we are assuming that x plays a different role in the previous example. Here x is assumed a function of t, and therefore x prime, here when we write x prime, this has exactly the same meaning as if we had the derivative of x with respect to t, one derivative of x with respect to t, right? So we could have more, this is the first derivative of x, that could be a second derivative, third derivative, and that's also known as the order of differentiation. So, but we're simply trying to refresh our mind with two types of notation for derivatives. One of them is called the quotient notation for derivative, and the other one is prime. And we're simply emphasizing that it's important that we are clear which is the variable of differentiation when we're reading derivative information. Now let's comment a couple of examples of differential equations. Very importantly is that the derivative operator appears on the expression. It's called equation because there is an equal sign, right? That's the whole idea. Something is equal to something else. Here, this expression on the right hand side, okay, RHS, also another thing that will play a role. This expression here involves P, okay, it involves P and it involves T, okay. So you could write the right hand side simply as an expression of P, the function that's being differentiated, and the variable of differentiation. This, we're writing here this in prime notation. This would be also the same as if we write the derivative of P with respect to T. If we use the either quotient notation, then we would say something like that: dP dt equals f of t comma p, and that expression, this expression f in this case, is something that looks like rp times quantity 1 minus p divided by n. Okay, so this is a simple example of a harvested population, and well, we'll discuss this in more detail much later. But in terms of writing the differential equation, these are the different ways of reading and rewriting this equation. Another example has to do with a system that connects something that is going to look like this. It's going to be a system that has a mass that is connected to a spring, and there is a way of describing the distance traveled by this mass, and so we could assume that y denotes distance as a function of x, where x is time, and if we make that assumption, then we can write an expression like this. This is using the quotient notation of derivatives. It's also common to write this expression with prime notation, so we could write y double prime plus 0.9 y prime plus 2y equal 0. Another example of a differential equation is in the context of electrical circuits. An expression as appears here with the prime notation could also be written with quotient notation as second derivative of I with respect to t plus 4 times I equals sine of omega t. Okay, so we could write this equation in prime notation for the derivative operator, or we could use the quotient notation and write in that alternative way. And this next differential equation, some of these examples are chosen here from different contexts. Some of these equations are actually named after somebody. So in this case, this is a name, Van der Pol, and this equation is named after that person. So you could, there is explicit detail here. This is an example where usage of the prime notation is also enhanced by specifying what is the variable of differentiation. So we could write the same equation in short as y double prime plus mu times quantity y squared minus 1 times y prime plus y equal 0. So in other words, we could drop that parenthesis specifying what is the variable of the independent variable of that function and write this in terms of prime notation. It would look like that. Or alternatively, we could write the same equation using the quotient notation. And last but not least is an equation in which there is a function u, here a function u that is really a function of x and y. It's a function of two variables. And then these expressions that appear here, they are derivative operators in quotient notation. They come from this type of thing. So you want to think of this. This is approximately another way of writing the derivative with respect to x. Here on the right hand side, we write the letter d, lowercase d, d as in derivative. And here the symbol looks like the letter d, but it's not exactly that letter d. So this denotes a so-called partial. Okay, it's called partial derivative. If you have never seen this, do not worry, because it means exactly the same. You're taking a derivative. The definition of derivative in terms of a limit is basically the same definition that applies for a partial derivative, but the important thing is that we use partial derivatives when the function is a function of more than one variable. And this equation here is an equation that is also named after somebody. It's called Laplace equation. So there are other ways of writing. Sometimes people would write the derivative operator as a subindex. They could write something like u sub xx plus u sub y equal to 0. And that is a way of not using the quotient notation and using this other type of notation. So differential equations are one of two types. One type is known as ordinary differential equations, and the other type is known as partial differential equations. The latter is going to use the partial derivatives we're just discussing, this type of differentiations. And this one, ordinary differential equations, this is also known as ODE, right? So differential equations, one way of referring to this branch of mathematics is saying Diffy Q's. That's how ordinary differential equations is known out in the streets, all right? But formally, the acronym for ordinary differential equation is ODE, okay? So that's what we will spend studying and learning over the course of several weeks. We're going to dedicate efforts that are entirely devoted to ODEs. So examples of ODEs include the harvested population growth, the spring mass equation, the RLC circuit, and the van der Pol equation. And an example of a partial differential equation is the Laplace. But so in ordinary differential equations, the functions that are unknown are the unknown functions are basically, that's the goal. Solving the equation means that we would find the function that is unknown. So for example, in this case of harvested population growth, here we would like to find, okay, we would like to find P. P is a function of time, and the goal is that given the ordinary differential equation P prime equals Rp times quantity 1 minus P over n minus h, we would like, given the differential equations, we would like to find P. P is considered the unknown. For the spring mass equation, the unknown function here is y, so we would like to, given that differential equation, we would like to find that function y. And similarly for the RLC circuit and the van der Pol equation, would like to find the unknown function. So in ODEs, the unknown functions are functions of one independent variable. In those previous examples, that was the case for P as a function of t, y as a function of x, I as a function of t, and y as a function of t. For the partial differential equation that we visited, Laplace's equation, that in such case, the unknown function u is a function of two variables, x and y.